Good evening, and thanks for joining tonight's TI Technology webinar hosted by Texas Instruments. Where tonight we're going to take a look at recreational mathematics and TI technology. My name is Mike Houston, and I'm the moderator for this event. I teach algebra and calculus near Pittsburgh, where I use TI technology to make those tough to teach, tough to learn concepts accessible to all my students. To help explain more about what recreational mathematics is, we have our two experts with us tonight, Ron Lancaster and Ken Collins. Ron is an associate professor at the University of Toronto, where he teaches mathematics courses for pre-service, middle, and high school teachers. Ron's professional activities include consultations and conference presentations around the world. He is the recipient of the 2015 Margaret Sinclair Memorial Award recognizing innovation and excellence in mathematics education, awarded by the Fields Institute. So Ron, it's great to have you with us tonight.
Thanks, Mike.
And Ken has a BS in physics and a master's in math and a PhD from Purdue University. He's taught for 55 years in middle school through graduate school. His focus is on effective use of technology and applying mathematics to analyze current issues. He teaches calculus and algebra 2 with extensive use of calculators and technology. He is currently writing curriculum material for classroom explorations in mathematics and using mathematics to analyze critical problems in our society. And also, as an added bonus for Ken, he is, I believe, going to be retiring this year after 50 consecutive years in education. So with that being said, Ken, congratulations, and thanks for joining us tonight.
My pleasure. Thank you, Mike.
We're expecting a large crowd, so your audio is muted. Feel free to send any questions to Ken or Ron using the Q&A window on the right side of your screen. We'll also be using the chat window to send general messages. As a reminder, the session is being recorded, and we'll provide a link to the certificate of attendance at the conclusion of the webinar. If you happen to have any audio issues, try selecting the audio broadcast button at the bottom of your WebEx screen. At this point, Ron is going to discuss our agenda.
I'd like to welcome all of you tonight to our webinar. It's a pleasure to do this with Ken. I wish that we were doing it in person together. But we have three things that we're going to do with you that involve recreational mathematics. One of them involves something incredibly simple with linear functions that you might never have seen before. So it's kind of cool. And it's not a lot of hyperbole. We're also going to do this thing with the four-number game. It's going to be low floor, high ceiling, very accessible, and then it's going to go to the moon. We're also going to do some incredible stuff with Pythagorean triplets that is like very accessible, but also goes to the moon, with the range. And at the end, stick around at the end because there's a webinar drawing that Mike will be doing, and there's a prize. I'm pretty sure that it's free registration for one of the summer workshops. Is that correct, Mike?
That's correct, Ron. Thanks so much. And Ken is going to discuss our expected outcomes.
Well, I didn't realize that one of our expected outcomes was going to the moon, Ron. You can tell me about this. I'm sort of befuddled here because I didn't write it down in the outcomes here, and now I think I'm leaving something out.
We'll just go in that direction.
Oh, go in that direction. Well, that's vertical, and I have trouble with height, so I'm just going to try to stay with my feet on the ground, and if you want to go to the moon, though, just do it after the seminar's over. Okay, that's great. So expected outcomes. Okay, so what we're hoping is that you get to see how to use recreational mathematics in your classroom. You can use it as a warm-up. You can use it as an enrichment activity. You can use it as a way to encourage collaborative learning and develop mathematical imagination. And we'll be sort of highlighting this as we go, unless we get to the moon first, and then we won't be able to do that. And then teachers will show how to use recreational mathematics to show that math can be a pleasurable activity, that you can have fun with it, and you can do it at all sorts of levels, and it's something that you can do as a lifetime activity. And hopefully you'll learn more about how recreational mathematics can give students a sense of joy and wonder by playing, tinkering, imagining things, maybe even going to the moon. I guess that's a possibility.
You know, that last one, Ken, ties in with a lot of the themes at the NCTM conferences these days. You know, they'll have strands on the joy of mathematics.
Yes.
Very exciting stuff, guys. Thanks so much. Ron, you have control. Feel free to share your screen. And
okay, thanks, Mike.
No problem. While Ron's doing that, we're going to do something a little bit different tonight. Typically, we don't give out the documents until the end. We're going to try and flip that tonight. So I'm going to post in the chat window a link for the documents that especially Ken's going to go through here in a few minutes. And if the link's not working, or if you have trouble opening the documents, or if there's any issues whatsoever, please just know that we will fix that issue down the road. You'll automatically get a follow-up email in a couple of days, and that will have a new link to look at. So again, if you can get it, great. If not, no fear. Ron, it's all yours.
Fantastic. Thanks, Mike. Just a quick note about Ken. So you heard that there was mention made of 50 consecutive years of teaching. Ken's actually taught for 55 years, but those 50 years, the past 50 years, have all been in the same school, the Charlotte Latin School. And that school opened up 51 years ago. So Ken has been at that school for almost the entire run of the school. So he's the history, the memory of the school. It's pretty amazing. I'm also retiring this year as well. So I plan on staying very active professionally, though. I think Ken as well, with conference presentations and whatever. But we're both kind of in the same moment right now. You know, Ken, when you think of recreational mathematics, I think if I looked at your library, this is part of my library here, I think that this says a lot about recreational mathematics if people were just to look at our books. But what would be a few topics that you would include in recreational mathematics?
Well, I think when I think about playing with numbers, I think of things like magic squares, and of course, right now, Sudoku puzzles are really popular, and frankly, I'm a Sudoku addict. I've got to have at least one good puzzle a day, just and sort of the day isn't complete until I've been able to do that. And I think also using your imagination to come up with things that are different, and and sometimes as teachers we get some weird questions in class, and but we have to quote cover the material, and we push them to a side. But sometimes allowing those discussions can actually get students real interested and lead to some great work and discoveries in the classroom as well as on your own.
Would you include games like Rush Hour and Set in recreational math?
Yeah, I would, Set would definitely be one I would include.
Rubik's Cube, for example?
Absolutely.
Yeah, origami?
Definitely.
Yeah. And I think, if I looked in your library, Ken, I think probably I would see a lot of books by Gardner. So,
yes.
Right. And I think for any teachers looking for more material, I think that, these are worth getting. Books, you might not get the print copies. The Mathematical Association of America has a CD that you can purchase, probably in different formats as well, but it'll give you a great deal of material in recreational, mathematics. I think there's one common theme that Ken and I would both agree that runs through recreational mathematics. It's a really tough thing to define, but I think the common theme to so much of it is playfulness. The idea of being playful. Some of you may be looking at this and thinking that I've misspelled that. That's the Canadian version of playfulness. We often say A. So, but it demonstrates the idea of being playful. But that runs through recreational mathematics. So we thought we would start off with a little example for all of you. And you can try this yourself as well and work with us. Ken, I don't think that I know you and I talked about this, but I don't think I gave you the set of equations. So what I'd like you to do, and everybody else can do this as well, is just solve the equation. So if you could take a moment and just do it. So Ken, what have you got as your answer?
Well, let's see. I get 2x equals -5, and dividing by 2, I get x equals -2.5.
Okay, yep, fantastic. And hopefully everybody else has got that as well. So, that isn't like a big deal. It's x equals -2.5. So Ken, the idea of being playful. So what I'm going to do is play with the coefficients and I'm going to interchange them. So what I'd like you now do is to solve this equation. You can see that I've switched the 3 and the 2 and the 5 and the 7. So what's the solution now?
Okay, so we get 5x equals -2, so x equals -0.4.
Okay. So you notice that I've switched the coefficients and everybody else does as well. But to the whole group and to you, Ken, as well, what do you notice about the solutions? And maybe, Ken, you could take a peek in the chat because it's hidden for me right now because I'm in full screen.
Okay.
Just see if anybody makes a comment. What do you notice?
Well, somebody's saying reciprocals,
No.
and another person's saying it also.
Oh. Anything else?
So they're both negative.
Okay, good. That's
And
fantastic, Ken. So you're absolutely correct. In this case, they are reciprocals. It's interesting that the way Ken gave me the solutions kind of hides the fact that they're reciprocals. So when you do this with your students, you might want to deliberately pick some numbers so that the fractions are rather awkward and your students reach for a calculator and provide a decimal answer, because then it's a little bit more hidden that they are reciprocals, from that. So now the big question from this playful exercise, is this a coincidence? Is it a fluke, that this happened? Or is it just this one case? Recreational mathematics is filled with a lot of flukes. Things like 1 cubed plus 5 cubed plus 3 cubed. When you work that out, it's 153. It's like a fluke, that happened. But it invites us to ask, when else does that happen? And so it's the same thing here. If this is a fluke, is it the only case in the world where this happens, or are there more? So Ken, how would we do this?
well, we could try using other numbers and maybe even try to do it in a sort of a general case, so it's not necessarily number dependent.
So the general case, what are you thinking of?
Well, instead of having those coefficients like 3, 2, 5, and 7, what happens if we just put in A, B, C, and D?
Oh, okay, yes, yeah. And by the way, Ken, one thing in the chat, I'm actually surprised that nobody mentioned this. I mean, maybe this is a fluke because if you look closely at the numbers I chose, 3 plus 2 is 5, 5 plus 2 is 7, right? There's, those numbers don't appear to be just random.
Mm-hmm.
So maybe that's why it's working. So Ken, if we're going to do the general case, do you want to show everybody how to do this with Nspire? So I
By
guess
the
you're
way,
going to do,
somebody mentioned that the numbers are all prime. The coefficients are all prime too.
so maybe that's why this is
Yeah.
working, right? I mean, I can be a bit of a sneaky guy at times, and maybe that's why this is working. I'm kind of pulling a fast one on you. I've carefully chosen, these prime numbers and these combinations so that this works. But I think Ken will lay this to rest. Ken, I'm going to give you control here so that you can use Nspire to actually make a decision here about this. So you should have the screen now. And
Okay.
so maybe you could use AX plus B equals CX plus D. So that's going to be what you're going to solve.
All right. So,
I'll need to see Inspire, Ken. Yeah, good.
okay. So,
And I've seen your Word doc. Good.
okay. So let's see. One of the things you have to be careful about is I can't just write AX. I have to write A times X. Because if I write AX, then it might think that AX represents a new variable in and of itself.
So Ken, you've just resolved something. The reason I've asked you to do this is because 5 minutes ago, before we started, I was trying this. I did solve, blah, 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 and it wasn't working. But I can't believe this. I forgot the negatives, the multiplication signs. So do you need a solve command?
Okay, so I'll write the equation. Okay, and I'll solve this for X. All right. So let's see.
Oh, Ken, is it
Yes.
because you called later on you have matrix A?
Ah, yes. Okay. This is.
Why don't you use
I tell you what. I'll do a new.
PQRS?
Yeah. Okay. So I'll go ahead and
I can't believe I forgot that multiplication sign, Ken.
well, I forgot that I had defined A as a matrix earlier in the document. I just pulled up the document that I had.
Yeah.
So that's what happens when we get old, Ron. You know, that's just the fact of life. Okay. All right. So there it is.
So Ken, what I'd like you to do then to lay this to rest is can you do BX plus A?
Yeah,
then
and I can
DX.
pull it and copy it. It makes it much quicker. All right.
So Ken, was it a fluke?
Well, it's not a fluke as long as A and C are not equal or B and D are not equal.
Beautiful. That is beautiful. Yeah, so it's actually a gorgeous result, you know, that this happens. And one of the sweet things is that Inspire allows you to do this kind of thing. Now, you might argue that maybe this is something that, you know, all students should be able to do. But on the other hand, if you're in a class with a lot of mixed abilities, there may be students that just have a lot of trouble doing this kind of, you know, solution with the literal coefficients. And so Inspire allows you to do it. Ken, if you give me back control here, we'll take a look at our document here.
Okay. So, all right. So I've stopped sharing. And so for you to get control.
Yep.
Okay.
Good. Yep. Fantastic.
I can.
Okay.
Great. Thanks, Mike.
Thanks, Mike.
So, so what Ken just did is he took those two equations with the coefficients flipped around, and those are the results. And so clearly it's not a fluke under the conditions that Ken mentioned. We found this actually in a great newsletter. I'm going to give you a moment to copy down this email address. Chris Smith is a mathematics teacher in Scotland, and he puts out a newsletter every week. And this is a must-have for teachers K to 12. There's always good stuff in this newsletter. So if you write to Chris, you can tell him that you were listening to Ken and I tonight and that you want to be added to his list. He's not going to sell your email address. This isn't a commercial venture. Chris has been doing this for a long, long time, and it's just a labor of love. But you will just get a ton of great material, you know, from this. So that's where we found this idea. What Chris did in his newsletter is he just had this as kind of an oddity, like, hey, here's an equation, the ones are reciprocal of the other. So Ken and I got thinking about this, and we thought it would be nice to try and turn this into an activity. So here's an idea. What you could do is give every one of your students a pair of equations. So one student gets 3x plus 2 equals 5x plus 7, and they also get 2x plus 3 equals 7x plus 5. And have your students solve both those equations, and then take the solutions and turn them into a point. So in the end, every one of your students gets a point. And then you collect those points, you aggregate them. They go into a Google Sheet, they go into Nspire, they, whatever. They get plotted on a great big piece of chart paper or something. All of these points. So, if you have 35 students in your class, you're going to have 35 points, from your class. And so you take all of these together and plot them. Now, you already know the answer to this, that there's a reciprocal relationship here, so that x2 equals 1 over x1. But at this stage, your students would know this. And so that's what they're going to get, when they plot all the points, and do that. They'll get a graph of y equals 1 over x. And then at this stage, it could be, why did this happen? What was the reason behind this? This file, by the way, I created in Sketchpad. I'd like to invite all of you to think about how you would do this in Nspire. It's not that hard in Nspire, to do this, to set up something where you have a spreadsheet in Nspire that collects all this information and then graphs it, to get that. So that's a little something for you to use. The next thing that Ken and I want to do is tell you about the Ducci sequence. Because recreational mathematics is filled, tonight we're going to be doing a lot of things with numbers. But recreational math is a lot of stuff. We just thought we'd focus on numbers tonight. Ken, do you want to tell everybody about the 4 numbers game, the Ducci sequence? It's also called the Diffie frequency.
So if you take 4 numbers and you subtract them in succession and take the absolute value, so you always get a positive result, then you'll get 4 new numbers. So if you take that top row of numbers that Ron has there, and if you subtract 16 minus 42, you get negative 26, and take the absolute value. 24 minus 42, negative 18, take the absolute value. 38 minus 24 is 14, and 16 minus 38, negative 22, take the absolute value. And so that gives us 4 new numbers, which we obtain by taking the absolute value of the difference of the first row of numbers.
Beautiful.
And then we could try it again.
So you get a 3rd row, a 4th row, and a 5th row.
Yes.
By the way, for those of you teaching middle school, if you don't use the absolute value, you don't teach that, of course. Another way of saying what Ken said is to get the 26, look up, look to the right, and take the largest minus the smallest. So you would go 42 minus 16 and get your 26. To get the 18, look up, look to the right, do the biggest minus the smallest. So it'd be 42 minus 24. So you could explain this without absolute values, if you would prefer. So Ken's described the game to you. So you work out the next row and the next row and the next row. And there's a general formula for this. And you keep going. And so you just keep going and going and going. Ken, how does this game end?
Well, if we can get all zeros, then at that point on, if we keep subtracting, we'll get zeros. So that would be a reasonable way to say the game is over.
Okay, so it'd be something like this. So that example that Ken and I have started off with, after 4 steps, we get a row of zeros and we're stuck at the zeros. It's kind of much ado about nothing, in this case. And we talk about the length being 4. So it's like four numbers. It's like a function, really, the length of it being four. Ken, and we could maybe do this in the chat as well. So for everybody in the chat, what questions do you have about this? So particularly if you haven't seen this sequence before, what are you wondering about, with this? Do you have any questions about this? Are you curious about anything? So what questions do you have about this? By the way, there's a geometrical representation as well. So you can also draw it this way. You put the four numbers at corners of a square, and then you kind of keep working your way inside. Ken, do you see anything in the chat? Is there anything that people are wondering about?
One thing is, can we find four numbers that sort of don't get down to the zeros?
Oh, okay. Yeah. Great question. So that's a great question. Anything else?
If you put four other numbers there and it gets down to zeros, do you know how many rows it takes to do it?
Oh, so you want to do a prediction?
Yeah.
Okay. Anything in the chat, Ken?
Well, those were two things that would come
That's great.
up.
Yeah.
And is there anything special about four?
Oh, mean four numbers that we're using?
Yeah.
Oh, that's beautiful as well. And I think in recreational mathematics, this is an important component. It gives students a chance to ask a lot of questions, to be curious, to wonder. I wonder what happens if we started with five numbers and played the five-number game or the six-number game. Ken, is there anything else in the chat? Is anybody wondering anything else?
Well, there's some people complimenting it, so they like the visualization and the numbers.
Oh, that's nice.
And then one question came up as to why did you choose only even numbers?
Ah, very nice. So maybe it only works with even numbers. Maybe that's why. Maybe I'm being sneaky again. Maybe there's something about even numbers that if I would have included an odd number or all odd numbers, wouldn't work. So great question. Absolutely. Yeah, that visual that people were complimenting, that is really beautiful, isn't it? I mean, you could picture this in a classroom or in your hallway, having to set up. You could use stickies and put them up, and make the squares, or, put this up in a large space in a wall and have a QR code beside it so that people could, tap it and, get a video or something explaining it.
Another question that came up is what happens if you were to use negative numbers?
Oh, lovely.
And then somebody wondered if you could put it on a spreadsheet.
Beautiful. Absolutely. Or use Nspire as well, or write a program, for Nspire or for the TI-Nspire, that would spit out the answers for you. So
and then there's an exploration question as to where you got your t-shirt.
So this is from Luta Fashions, and it's social distance, of course. It might be hard for you to see, but there's actually a mistake in the shirt. I bought this months ago and they have not corrected it, in spite of the fact that I've hounded them. They're missing an X1. And I complained, and I said, I don't want the shirt. It's got a mistake. And they wouldn't take it back. But I still recommend the shirt because it's really cute. So it was Luta Fashion. I didn't realize I'd be a fashion statement tonight, Ken. So
for somebody who wants to go to the moon, that's the least we can expect,
Yes, yeah. So, these are great questions. So, is it possible for the game to never end? Or if it always ends, how would we prove that? And the idea that somebody asked about, how does the number of steps that it takes depend on those four numbers? I don't think anybody asked this one, but it's a nice question. Is it possible to find four numbers for which the game takes a long time to end? And what about using fractions or decimals? So somebody asked about integers, but what about irrational numbers? What about complex numbers? Complex numbers are a problem because if you're going to do the biggest minus the smallest, you have no ordering property with complex numbers. So these are some great questions that you can pursue with your students. And by the way, the issue of finding numbers that take a long time, good luck. If you open up a spreadsheet right now and you just type in any four numbers, you are going to really have a hard time finding four numbers that take a long time. I mean, I just tried huge numbers here. 4 steps, the row of zeros, and the bottom one as well. So it's really tough to find four numbers that take a long time. Somebody asked about the 3-number game or the 5-number game or the 6-number game. We can't go into this tonight, but here's a shocker. The game we're going to divulge something. It turns out you always get a row of zeros. So if those four numbers are any integers, fractions, decimals, you always get a row of zeros. And the proof is actually not that hard. If you look up the 4-number game or the Ducci sequence, you'll find a lot of stuff, that talk about the proof. But here's the kicker. The 4-number game only works. Ken, what are those numbers? 4-number game, 8-number game, 16-number game?
Those look like powerful numbers.
They do, don't they?
Yeah.
Absolutely. It turns out it's only powers of 2. If you play the 3-number game, sometimes you might get zeros, but other times you're not. So you don't always get the row of zeros. So it's powers of 2. It's a very strange thing. So, why is that? And what you can do with your students is a lovely investigation where you take 4 consecutive terms of some sequences. Take 4 consecutive odd numbers, 4 consecutive terms in a geometric sequence, 4 consecutive Fibonacci numbers. And you can have your students do an investigation, with this. This is a really pretty one. So this involves a geometric sequence, 1x, x squared, x cubed. And it turns out there's a really strange thing. The x equals 2 takes more steps than all the others. And why is that? So it's absolutely gorgeous. Ken, how would you do this algebraically? How could you work this through to find out, like, why is it that x equals 2 is the odd one out?
Well, you would, if you just wanted to make it general, you could make that top row 1x, x squared, x cubed.
Okay.
And if you want to do, and
But how
then
do you-
since we
how do you
know
know
if
which
you
one's
want to
bigger?
make x greater than 1, so 2 or something greater than that, then we know that the next one would be x minus 1, because that would be positive. And then x squared minus x, and x cubed minus x squared, and then x cubed minus 1. So we
So
would
how
know,
do you know that it's x cubed minus x squared? Why is x cubed bigger?
well, because if x is greater than 1, then you're multiplying x squared by a number greater than 1 to get x cubed.
Beautiful. Lots of great reasoning here. That was really cool, Ken. So now what are you going to do? So, how do you know whether x cubed minus x squared is bigger than x squared minus 1?
Well, actually, we could, x cubed minus x squared is x squared time, well, that's bigger than x minus 1. So if we factored out an x, and then we get x squared times x minus 1, and then we could take a look at x minus 1 times x plus 1.
Oh, that's beautiful, Ken. Everyone has a
Yeah.
factor of x minus 1, doesn't it?
Yeah.
Yeah. You just
And then you
cancel
could
them off.
compare the other factors, and they're going to be bigger.
Beautiful. We won't finish this off, but if you do, you're going to find you're going to get to a step where trying to figure out which one is the biggest, it splits. X equals 2 is one way and x equals not equal to 2 is the other way. So we'll leave this with you to do, to take a look at. I'm going to just wrap this up because just a couple last things about the Ducci sequence. This is a great opportunity for coding. So if you want to have students look at the Fibonacci sequence, if you haven't seen this before, the first three numbers are arbitrary, 1, 1, 2. That's usually what's used. And then you add up the three numbers to get the next number. So it's called the Fibonacci sequence. But if you want your students to do 4 consecutive Fibonacci numbers, do you want to do these by hand? So the coding is fabulous. So this will be in the, Michael will be making this, Michael, make this available to you. But it's a program for the TI-Nspire. And when you run the program, it'll tell you. And here's a shocker. 4 consecutive terms from the Fibonacci sequence, they take a heck of a long time. I mean, take a look here. 36 steps, 48 steps, 51 steps, 57 steps. There's something going on here. Because folks, it is really tough to find 4 numbers that take a long time. But there's something cooking here. And you'll be able to go into this PowerPoint file later, and you can actually go through and learn more about this, about what's going on. There's a great opportunity for patterning here and all sorts of stuff with this. So it's really cool. So Ken, I'll let people kind of go through this and, at their leisure. And the business about going to the moon, this is like, oh my God, like what's going on here? Like you've got these equations here, x cubed minus x squared minus 1, and it's like, so it starts off very, very easy, but then it just takes off, from this. So, anyway, Ken, I'm going to turn it over to you. I'll let people take a look at this at their leisure. And I've also got some recommendations for you in this PowerPoint file about a couple of journal articles as well that you can do. So Ken, I will give you control here. And there you are.
Okay, thanks, Ron. Okay, so I'm going to go ahead and.
Great. While you're doing that, Ken, I'm going to just grab something here.
Okay. All right. So last December, some of you might have remembered that the 16th of December had a interesting date to it, 12/16/20, and it was a 3 numbers that form a Pythagorean triple. And it was also one of the last school days that we had in the fall semester. And we were doing a hybrid teaching situation, which I must say this year of teaching has been one of the most interesting and exhausting for me in over half a century. And I'm sure for many of you, it's been the same way. And so rather than trying to squeeze in one more math lesson, I noticed this date and I said, I promised the students we would be doing something fun on the last day that we were going to have classes, and that it would be mathematical. So so I'll tell you what, as we go through this, what specifically we did in addition to this, that the students enjoyed and was something that they could work on further over the holidays, which they were happy to do. But anyway, so of course, you're probably aware about Pythagorean triples and that they are satisfy the Pythagorean theorem. And so the 12/16/20 does that, but it's not a primitive Pythagorean triple. So a primitive Pythagorean triple would be like 3, 4, 5, because it doesn't have any common factors other than 1. And but if you take any primitive Pythagorean triple and multiply all the numbers by a constant, you'll get another Pythagorean triple. And And this is the sort of thing, this is what I love about these type of explorations, is that you can do this with elementary school students and they could check out to see whether out that really works. You could do it with high school students, and say in a geometry class, and then say, okay, could you show in general why that has to be true? And it's really not hard to show that, if you multiply by some constant and then take the sum of the squares of the two smaller ones and combine them, you get the square of the larger one. So, but again, it's one of those things that can be done at many different levels. Okay, so so we started constructing what we call a ternary tree. So that's a tree that has no more than 3 branches coming from each branch before it. It's sort of like a computer science thing with nodes. And about 90 years ago, there was a mathematician who discovered that all the primitive Pythagorean triples can be arranged in a ternary tree, okay? And so we could start with, say, 3, 4, 5, and then start creating more primitive Pythagorean triples from that. And as a matter of fact, one way of doing this was to take a look at some matrices. So Barning showed that if you use these 3 matrices, A, B, and C, and then take, say, a primitive like 3, 4, 5, and apply through matrix multiplication these 3 matrices to that Pythagorean triple, then you get another Pythagorean triple that is primitive. And so this was in an Algebra 2 class, and we had already done some work with matrices. But if you're dealing with a younger class, it's not that difficult using a 3x3 matrix to do the multiplication, and they can sort of see how to do that. If it's a younger class, you can allow them to use technology to get the results of doing a matrix multiplication. So this can be adapted at various levels.
Ken, those matrices, I'm still wrestling with this. I find this stunning, but could you just show me those 3 matrices again? Because people might want to just take a peek at these. I think they're called unimodal, these matrices. I suspect, you can tell me if I'm correct, but I suspect the determinants they're all 1.
Or perhaps -1.
Oh, okay. Yeah. And I've also noticed, is this a coincidence that it's like all the same numbers, but it's just got minuses and pluses kind of thrown around here?
Well, not randomly distributed though, if you're. So
okay, no, but I mean in the middle column, I see a 2, 1, 2 and a 2, 1, 2 and a 2, 1, 2.
Yes. Yeah.
Wow, that is like really cool. Yeah. I think everybody probably will want to take those matrices and see if they can kind of think about where they come from, or what patterns they see in the matrices. Even that alone is an interesting question.
Yes, and the fact that the only difference among the 3 matrices is that in A and C, one of the columns is negative, and that doing that actually in each case causes you to generate another primitive Pythagorean triple.
So could I do the same thing by changing all your 2s to 3s?
Well, we could try that.
No, I don't mean to interrupt here, but
but
I'll try that later.
My gut sense is that might not work in terms of maintaining Pythagorean triples.
Okay.
But that's what's great is that's one of those what if questions that if I were doing this, say, with Nspire, and I'll show a few things with that, it would be very easy for me to go ahead and change any one of those matrices and replace the 2s with 3s and then just see what happens.
Beautiful.
Okay.
By the way, just a quick note to everybody, Ken. I'm not sure why, but my chat is disabled. So I'm attempting to reply to people, but the chat is disabled for me. So Maybe Mike might be able to clear this up for me. Sorry, Ken.
Okay. Okay, so we go ahead and, go through this actually was a little bit of a review for some of my students. One of the things that I noticed this year, and especially last spring we were totally remote for after mid-March. This year we were hybrid, so half came and half were remote. And what I found was it was much more difficult for students to develop long-term memory concepts of things when they were remote. It was just hard for some of them, and I think we learned some important lessons this year about that. But anyway, so then I gave them the opportunity to go ahead and apply the matrices B and C to those 3, 4, 5 Pythagorean triple and see what they got, and then they could compare that with the results here. And so we've got our first 2 tiers of the Pythagorean tree. And just as an aside here, I didn't include this in the handout, but there were a lot of things that I had interspersed so that they could make tree decorations with these different Pythagorean trees, and then hang them up on their tree, or some of them did a couple of them, made a table, and then had put them together in various configurations. So it became sort of an artistic problem, and a lot of them, played around with it over vacation, because they just got sucked into it the way, some of us get sucked into Sudoku puzzles and stuff like that. So anyway, then the next thing they had to do was to go ahead and apply matrices A, B, and C to each of these primitive Pythagorean triples and get 3 more from each. And I'm not showing that in the handout, but that's something that the kids did on their own, and some of them finished within the class period. So I on the sheet that I gave them space to do their matrix work, and then I had another sheet where they could actually put the summary and color it and stuff like that. So that was all there for them. But then they started asking questions. They wanted to know, sort of, Ron's version of, am I being sneaky? Was I choosing Pythagorean triples that just happened to work for these matrices? But if I chose some weird Pythagorean triples that were, bigger numbers or something else, then maybe this would break down. And they said, well, can you show us that it's going to work for any of them? And I said, well, if you stacked all the primitive Pythagorean triples up, you could go to the moon, Ron. So that would be one way to get there. And I said, what about if we just say, let's take a general Pythagorean triple UVW, we could put it as a column matrix, and go ahead and say that U squared plus V squared is W squared. So that, or we could say alternately that U squared plus V squared minus W squared is 0. And I said, okay, so what would happen if we first tried it by hand? So we did that, and we took the matrix A times UVW, and then we got these terms for the matrix multiplication. And then I said, well, we could take the square of the first and the square of the second, and then if we subtract the square of the last, that should give us 0 if it's a Pythagorean triple. And this was the end of the first semester, and they really did not feel like going through that algebraic swamp to get there. So I said, okay, let's go ahead. We've got a CAS calculator. Let's set it up and see with the computer algebra system what we would get if we were to do that. And so we did that. So after we got this result, we took the square of the first of the numbers and added the square of the second and subtracted the square of the third. And what it simplified to was u squared plus v squared minus w squared. And of course, we knew that u, v, and w were Pythagorean triples, so that would simplify to 0. And so it looks like if we apply matrix A to any of the Pythagorean triple, we would get another Pythagorean triple. And then we checked it out with B and C as well, doing the same thing. We took B times the UVW vector and multiplied it out, and then took the sum of the squares of the first two minus the square of the third. And again, it reduced to something that's equal to 0. And so that happened with matrix C as well. So, and again, that's, this is the sort of thing that you can do at different levels. So these are students who are, fairly good students, sophomores mostly, second year of algebra. And so, this is something that they were comfortable with. If I were doing it with a middle school class, I might stick to just numerical examples and, just see, if anybody can come up with that one that doesn't work. Okay, so let's suppose we just take a look at one of these matrices and say, all right, suppose we just keep applying one of the matrices. Is it going to give results that form some particular pattern? So when we started with matrix A, so the 3, 4, 5 right triangle has many special properties, and one of them is that it's one of those Pythagorean triples where the largest number is one more than the second largest number. Or if you're thinking of this as a right triangle, the hypotenuse is equal to the largest leg plus 1.
Well, there's a lot of those, aren't there, Ken?
I'm sorry?
Like there's an infinite number of those kind of right angle triangles.
Yes, you're right. So that's another thing you could use to go to the moon. Okay, so that's good. All right, so if we apply A to 3, 4, 5, we get another triangle that has that characteristic. So if you apply A to that one, then we get the next one. And if we apply A to that one, we get the next one with that characteristic. And that continues all the way down the line. Okay. And then one of the things that you can do is, well, can you make a generalization of this? If I make 3 a Pythagorean triple such that the hypotenuse is one longer than the leg and applied A to that, will we always get a result of a similar fashion? And so that's one of the, the kids asked about that. And I said, well, maybe that's something that you can explore. I'm not going to answer all the questions. And you can try that yourselves. And some of them did. If we try it with B and C, it's not as obvious that we get something special. So that's okay. It works with A. It doesn't seem to do anything special with B or C.
But Ken, it might be that there is something there, but we just,
Exactly.
we can't see it immediately.
Yes. Yeah, so we could, take a closer look and see whether, there's something special in those relationships that's being maintained from one to the other. But in terms of just looking at it, it's not as obvious as what we saw with A.
I am noticing in your first example, the 3 and the 21, it's 7 times. The 4 and the 20 is 5 times. But then it falls apart.
Yeah.
Oh yeah, it doesn't. Yeah, there's no. I don't see the pattern, Ken.
That's okay. So so let's go ahead and take a look at one of the ones with another type of Pythagorean triple. So it's one where the hypotenuse is 2 more. And so if we try A again and continue doing it successively, we continue to get a sequence of right triangles where the hypotenuse is 2 more than the largest leg. Okay? And again, if we try with B or C, we get some interesting patterns, but it's not of that nature.
Wow.
So again, A is doing something that for whatever reason B and C are not. And you asked about the determinants, Ron, and so you were right. The determinants are 1 or -1.
I think I only was thinking of that because I remember something about these unimodal matrices.
Mm-hmm.
Forgotten kind of exactly what they are, but
Yeah.
something about the determinants being, kind of I thought it was always 1, but obviously not.
So so one of the things that I asked the students is because we had been dealing with inverse matrices also, is what happens if we go backwards? So if we know, for example, when we go up here with matrix A, so if we apply, say, matrix A to 8, 15, 17, we get this. So if we applied A inverse to this, we should get back to 8, 15, 17. And that's easy enough to check out. But what happens? So here are the inverses for A, B, and C. What happens if we take the 3, 4, 5 and ask a question? Well, what would be the Pythagorean triple that generates 3, 4, 5 if we use matrix A? So in other words, if I took A inverse and applied it to 3, 4, 5, what would I get?
Well, Ken, that's a right angle triangle too, if you allow degenerate triangles.
Well, I don't like to be degenerate, Ron, but yes.
Oh.
But you're right. It's u squared plus v squared equals w squared. Okay. And if if we look at this in terms of orienting the triangle, say horizontal, vertical, and the hypotenuse, this would look like a collapsed triangle with a length of 1 going to the right of the origin. And if we continue doing that, some really curious things happen. We get another one of those triangles, which looks like it's collapsed to the left of the origin, and then suddenly we start getting these Pythagorean triples, but one of the numbers is negative. So like this is say maybe in quadrant 2, going 3 to the left, 4 up, and then the hypotenuse is 5. And so the question is, well, can we sort of expand on our definitions to start allowing things like this to be considered as Pythagorean triples? And then what happens if we use the inverse of B or C to do this, and we get some similar results? And yeah, so now we're really going into uncharted waters. So this is not something I had any clue about until I just started to play with it. And that's what happens when you fool around with this stuff. You just start saying, well, what if we do this? What if we do that? And suddenly you start, it's like Alice in Wonderland.
That's one of the things I like about recreational math, and is
Yeah.
that there's so many opportunities like that to, actually make a discovery.
Yeah.
Maybe not something that was never known, but your own personal discovery.
Yeah. So anyway, as a resource, we have some primitive primes here, and then Wikipedia has some really nice resources that I use to do some of this. And then finally, I ask my students, when's the next Pythagorean triple date, and how old are you going to be? And I told them I am not answering that question. That's something they're going to have to work out themselves.
That's
So,
beautiful, Ken.
yeah.
We hope that you've got some ideas here tonight that you'll be able to use with your students. recreational mathematics is a real gold mine. Don't forget about the Martin Gardner books, things like that. Mike, I've emailed you Dropbox links, a link to a Dropbox file. It's kind of temporary. I know you're going to be posting this, but go ahead and give it to people now, because it seemed from the chat that people would like to have it now. So you're more than welcome to give it to them right now.
Yeah, I don't unfortunately have a good way of doing that, but we will get all the files together.
Can you not do that in the chat? Just put the link in the chat?
I can, you're right. So you said you sent me the Dropbox link?
Yeah. Because I noticed in the chat there were some people wondering if they could have it now.
Yeah, I didn't see an email from you, Ron.
I mean, if for some reason you don't want to do it right now, it's fine, but I just thought
I just don't see an email from you, Ron.
Oh, okay. Okay.
We'll again, we'll get this all together. We'll get the link fixed. I apologize for that. And within a day or two, we'll send out a follow-up email, and that follow-up email will contain a link to the recording so you can watch this again at your own pace, a link for all the documents, and a link for the certificate as well. So we mentioned early on that One Lucky Winner tonight is going to receive a T-Cube Summer Workshop registration. To learn more about the summer workshops, please visit our website. They are virtual this summer, and today's lucky winner is Lisa Hamling. So Lisa, congratulations. We hope to see you at a T-Cube Summer Workshop as well as everyone else.
Go, Lisa.
And to receive a certificate of attendance, let's try this link. Go ahead and click the link in the chat window. That should give you a link for the certificate for tonight. And if you're watching this on demand, go ahead and copy that link into your favorite browser to receive your certificate. Big thanks for teaching me something. I've done a lot of these, and it's really kind of neat whenever I get the chance to learn something. So thanks so much to Ron and Ken for teaching me something new about mathematics and ways that I can use it with my students. So thanks so much, guys.
Thank you, Mike.
Thanks, Mike.
For the audience, Ken and I have been teaching a course in recreational mathematics at the Phillips Exeter Academy Conference for some years, and we'd love to see you there. We're hoping the conference will run next year.
And thanks to everyone for joining us tonight. And again, congratulations to both Ken and Ron on their upcoming retirements.
Thank you.
Thanks, Mike.
Thanks, everyone. Have a great night, and we'll see you back online next week. Have a great night.